Okay, students, here we are on board again with some GIS basics work. Today we're going to be working in Appendix A, and we're going to be focusing on coordinate systems. The coordinate systems are an essential part of understanding the map world, the cartography world. So we're going to spend a little bit of time here, a little bit in the, what do you call it? Kind of like the theoretical world, and then a bunch of time in like the practical world, like when do coordinate systems cause us to trip up, or what do we need to watch out for, what coordinate system should we choose for a given map, that sort of thing. And so we're gonna get started here with some data to download. So we'll download our data, and I'm gonna save that like we always do, and we'll open the folder it's contained in, cut it, and then we'll paste it into our folder for this class. In my case, it's my demonstration folder under GIS Basics. Paste it here. And then in order for GIS to see it, I got to extract it, get it unzipped there. And once it's successfully unzipped, I can delete it there. Okay, so now I've got the stuff that I need. All right, and oh, let's see here, right. I know my deleted files will be deleted. The next thing, I'm going to pause this for a second because I got to pull up my PDF with our work in. All right, I got my PDF opened so that we can take some notes, talk through things together. So we're going to start out here just kind of in theory land with our notes for a little chunk of time, and then we'll open up ArcGIS Pro and do some map making. So the first thing we want to ask ourselves, what I want to ask you specifically, is if you wanted to find a specific location on a globe, what information would you need? So I pause for you to ask yourself that question, like, well, what would you need? If you were to plop a dot like somewhere in what we know as Greenland, how could you tell somebody where that was? And sometimes I'll have students in class do this exercise where I have them stand up and I say, you know, I give them directions. I say, go 3. And they're like, what do you mean, go 3 what? You know, and in which direction do you want me to go? You know, so you need to know kind of a sense of direction. To have a direction, you have to have a starting point, like start from where, okay? So the first thing you need to find a specific location on a globe is a starting point. And this is known as the origin, okay? So you have to know where you're starting from. And then you have to know, well, what direction are you going to go? And to know which direction you're going to go, you have to have axes. So they define directions. And for us, we have east, west, and north, south, because that's how we break up directions typically on our planet. And then the last thing you need, so if I told you to go 3, you'd need to know, well, where am I starting from? And define some directions for me. And you need to know units of measurement. So like 3 steps or 3 feet or 3 jumps if I'm giving you physical directions. And the axis, if like we were in a classroom and I was saying, you know, a certain direction, I could say toward the door or parallel with the wall or something like that, right? That would give you a direction. And on our planet, we have axes we set up. So units of measurement, okay? This is okay. Move this around a little bit. There we go. Okay. So we need 3 basic pieces of information in order to find any place. And that is, we need to know where we're starting from, we need to know what direction we're moving, and we need to know the units of measurement for our travels. Are we traveling in miles or meters? That sort of thing. Okay. So we can satisfy all of these requirements with a traditional Cartesian coordinate system. That's what this is called, a Cartesian coordinate system. You've seen this a bunch because half of your high school math is probably based on this sort of thing, right? And but it's if you didn't know the name of it, you probably do, but it's called a Cartesian coordinate system. And it's basically we've got an origin, right? And we've got axes. We've got an up and down and a right and left axes, right? And then our units of measurement are these little squares. So 1, 2, 3, 4, 5, 6 squares. And we can find ourselves anywhere in this space based on a defined set of coordinates that depend on these axes. Now see, so 3, 4 is located right there. So we can place ourselves in space because we know where we're starting from and we've got axes. All right, and units of measurement. All right, so that's what we need. A coordinate system. They're required to find ourselves in space. So basically, you need to know that all spatial data have a coordinate system. There's no such thing as spatial data that don't have a coordinate system. All spatial data are created with a coordinate system, whether you collect it in a GPS, whether you collect it on a Venza, whether you're putting points on a map. There's a coordinate system behind that, and that coordinate system is going to have an origin, axes, and units of measurement. Okay, so let's talk about some of the pieces of a coordinate system when it's dealing with our Earth. And that gets a little bit more complicated than a flat sheet of paper, right, in a Cartesian coordinate system. So if we're looking at our Earth, the actual shape of our planet is known as a geoid, okay? And so in our mind's eye, we might imagine that the Earth is a beautiful little marble, one of those marbles with green and blue. It's all peaceful. But in fact, our planet is lumpy and bumpy. It has things like the Mariana Trench and the Himalaya, right? So our planet isn't flat, and it is not smooth, and it isn't made of glass either. It's a geoid. So that's the actual shape of the lumpy, bumpy place that we live. But a lumpy, bumpy spheroid is really is tough, or a lumpy bumpy geoid is really tough to do math on, to define even units of measurement and to work with. And so what we do is we model our Earth to meet some of our mapping requirements. We smooth it out and kind of get rid of some of those lumps and bumps, and we call that a spheroid. It's still not perfectly round, but we have a few different spheroids. S-P-H-E-R-O-I-D. We have a few different spheroids that we model the shape of our Earth on, and we say, okay, for this, if we're mapping this section of the Earth, and like maybe we're mapping over Northern Europe, if we kind of smooth that lumpy geoid out like this, it works pretty well for matching up with Northern Europe, okay? So you're going to take the lumpy bumpy Earth, you're going to smooth it out, and you're going to add an origin, a starting point for your map, or a starting point for your system, okay? And then you need an x-axis, and you need a y-axis. And so once you have these things, you're ready to do you could do some mapping on the surface of the Earth. So you've taken our lumpy, bumpy Earth, you've smoothed it into a spheroid at an origin and an x and y axis. That process is actually that collection of things is actually called a datum, where you have the model that you've used to smooth the surface of the Earth. You've applied an origin to it and an x and a y axis. That's sometimes referred to as a datum. Okay. So if you end there, you're going to have a geographic coordinate system. So you've taken our Earth, you've kind of smoothed it out, you've put an origin, an x and a y axis, and that is called a geographic coordinate system. When we're dealing with a geographic coordinate system, our x-axis is the equator. And our y-axis is the prime meridian. Okay, and so you might be familiar with the equator, right? Is that it's the string snugged up around the middle of our chubby Earth, and then the prime meridian cuts through England. Because so much, well, why does it cut through England? Because that's the center of the map-making universe, because it was the center of the map-making universe, kind of. So when they set up a system for measuring things, they just set the north-south y-axis right through England. So there we go. So now you're completely oriented in space, but there's one more piece we talked about, that third piece from up above, and that is you need units of measurement. Okay. Looks like I'm staying capital here for a while. Units of measure. Okay. And what's interesting, or kind of interesting, or something to note, is that for a geographic coordinate system, and a geographic coordinate system is a system just like we talked about above. So you've basically just taken the Earth, you've smoothed it out, you've added an origin, an X and Y axis, and then you need units of measurement. For a geographic coordinate system, those measurements are in degrees. Well, let's talk just a minute about this. If you had math class with me, and only some of you would have, a small handful, we took a while to talk about why measurements of latitude and longitude are in degrees. And this graphic does a good job talking us through it. But if we look at the surface of the Earth, a 30-degree latitude means that if we are taking, we're creating an angle with the center of the Earth and a location on the surface of the Earth, and that angle is a 30-degree angle out of a total possibility of going from the center to 90 degrees at the top north, or the center to 90 degrees south, if we're looking at latitude. If we're looking at longitude, we can go from the prime meridian and we can open that up all the way to 180 degrees, all the way on the other side of the Earth. So the measurements, when you get measurements of latitude and longitude, and they're in degrees, they literally are a measurement of an angle. So just kind of make sure we're all on the same page there. It's not just, oh, we use that same word, degrees, but it doesn't actually mean a measurement of an angle. No, all the trigonometry that you ever learned totally applies to latitude and longitude, okay? We are working with angles there, okay? And then we're going to talk about projected coordinates in just a minute, but what they actually mean. But let's just briefly make sure you know that for a projected coordinate system, the measurements are going to be in either meters or feet, or usually just meters or feet, honestly. But they could be other things. But generally they're meters or feet. Let's see if I can make this line up a little bit better too. Okay, so basically a geographic coordinate system stops right here. They take that lumpy real Earth and they smooth it into a spheroid. They pop in a point of origin where you're measuring from, and then you've got axes, north, south, east, west, and units of measurement. Geographic coordinate systems are sometimes abbreviated. I'm just going to pop it right in here so you see it. GCS. So if you see GCS, I'm going to make that big just so it stands out for you guys. If you see GCS in a coordinate system, it means you're dealing with a geographic coordinate system, okay, GCS. Geographic coordinate systems, they're going to place elements on a map on that spherical Earth using latitude and longitude. Longitude, there we go, using latitude and longitude, okay? And then the units, what are the units of measurement for geographic coordinate systems? They're degrees. Okay, so you should have been able to answer that. let's see here. Oh, I did have a little note that I wanted to make that maybe I didn't show. Well, we'll maybe make it on the next page. Okay, so if the coordinate system that you're using in a given map is a geographic coordinate system, it's going to look stretched out east to west. And it kind of depends what scale your map is, how stretched out it looks. But let's see here. This is a map of Washington State, and it's in a geographic coordinate system, NAD 1983. And you can kind of see that it's a little bit stretched out east to west there. But if you look at this scale, if you're looking at the whole Earth, and this geographic coordinate system is WGS, it's called World Geographic System, 1984, and you can see that geographic coordinate system looks kind of stretched out east to west, especially if you look at, like this Alaska across Greenland to Siberia. This is the same geographic coordinate system, but then it's been projected. We're going to talk about projections in one moment using World Mercator. Something that you should know, and I should have made a little bit better, should have made a better spot for this, but we'll just type it in right here. And that is that you should know that geographic coordinate systems are not suitable for measurement. So GCS, geographic coordinate systems, are not suitable for measuring area. Okay, and they're not very good for distance either. Okay, and we're going to talk about some of the so when you're measuring with a geographic coordinate system, you're looking at measuring differences in latitudes and longitudes, differences in degrees, and we're not able to effectively do that. So you need to know that. We're going to pause. Okay, students, so we're back here, and we've just opened up our comparing coordinate systems. And what are we going to talk about? Well, let's talk about where we can find the coordinate systems and information about the coordinate system here in ArcGIS Pro. So we've got a project here. It has one map on it. At the end of the day, when we're done, we're going to end up with a lot more than one map here, but I've made this first one for us, and then we're going to copy it and do some changes to the coordinate systems. So first off, let's take a look at some information here. So I actually typed in this first one, GCS NAD 1983. And so GCS stands for Geographic Coordinate System. And then NAD stands for North American Datum of 1983. And so the North American, so the GCS reminds you, hey, this is a geographic coordinate system. So our measurements are all going to be in decimal degrees. And what you can see actually is if I move my cursor around the map, you can see decimal degrees show up down here. So that gives you a feeling for that. And then, what else did I want to say? And then NAD stands for North American Datum 1983, and that's a very common datum. And so what do we have there? We have a spheroid that's smoothed so that it works well over North America. We have an origin that works well. They kind of use they use a center of mass for the origin, and then they've got an X and a Y axis, and that's going to be our prime meridian and our equator. So, and that was developed in the 80s. And then I've got 4 Washington cities, which I've labeled on here, and I've got the counties in Washington. But what I want you to notice, when you look at this, you probably immediately think, that looks a little stretched east to west. And that's one way that you can kind of spot. I think that's a geographic coordinate system. They tend to have that elongated east to west look to them. So I've told you that, but how could you actually find the coordinate system of this map? The way you could do that is you're going to right-click on the map itself. So here's the map with 2 layers, but on the map itself, you're going to right-click and go down to Properties. And then the Properties, you'll look at Coordinate Systems, and it's going to tell you its current coordinate system is NAD 1983. And that's for XY, so we mean north, south, east, west. A Z coordinate system has to do with elevation, so if you're dealing with 3D data, and elevation becomes a component, then you'd have a coordinate system for the z data. I oftentimes like to stretch this pane out because what you can see here is of the coordinate systems that are available, you'll have your favorites if you've set some favorites. We're going to look at the coordinate systems of the layers in just a minute. And then the geographic coordinate system options are at the top. And if you open that up, you can see that there's different geographic coordinate systems that are suitable for different parts of the Earth. They will have different datums, and those datums fit well to that region of the planet. And so for us, we're looking in North America and Canada to find NAD 1983. Okay, and we're just using the straight up plain one. And USA and territory should also have NAD 1983. There it is. Same thing. It's just listed because it works well for Canada and for the US. All right, what else did I want to show you here? You can also see the coordinate system of the layers on your map. That's kind of a fun feature of GIS Pro. So it looks like we've got a couple coordinate systems for the layers. I just have 2 layers on my map. And there's one layer, the 4 Washington cities is in Clark 1866. And yes, indeed, folks, that is a coordinate system that harkens all the way back to 1866. I'm in awe of what humans could do. I'm in awe of what humans could do back in 1866, being able to, with such rudimentary measurement abilities and with computing that was all human by hand computing, being able to come up with things like coordinate system that works for the globe. And then we've got the Washington counties layer is in state plane, and we're going to talk a little bit about what projected coordinate systems mean. Let's just do that now. So I kind of wanted to show you a geographic coordinate system, but let's go back to our notes now. And I told you a geographic coordinate system is not suitable for measuring area. Let's talk about coordinate systems that are suitable for measuring areas. Let's talk about projected coordinate systems. And so every coordinate system has to start with a geoid that's been turned into a spheroid, smoothed, an origin, north, south, east, west axes, and units of measurement. That's just the starting point for everybody. But projected coordinate systems go a step farther. And so they take the surface of the Earth and they flatten it. But we call them a projection because the idea is that it's what you would see on a piece of paper if the Earth was a glowing orb, which is really kind of a pretty thing to think about. Imagine it kind of makes you want to get into art, like glass art, and create a globe, a glowing globe of the Earth. But if the Earth had a glowing center and you put a piece of paper around that glowing center, what would things look like if they were projected onto that? So way back in the way back, or like when you go to a movie theater, right, and there's a projected screen, it's like light being projected onto a screen. So that's what we're talking about. And when you think about that, the dimensions of each of the continents and kind of its shape is going to depend on where you put the paper. And so if you place that piece of paper right over the area you're going to map, like if we were to put a little dot on Spokane, the city, and lay a piece of paper on that, you'd get a pretty accurate picture of Spokane. But as you got further and further out from Spokane, you'd get distortion all around you because the paper is further from the actual Earth and the things that are projected onto it get stretched. And so so that's what we deal with. When we deal with projections, we're able to create an image of the Earth on the image of the very, spherical Earth onto a flat sheet of paper, which is very convenient, right? And then the trade-off is that we're going to have distortion in some areas of the map. There's a few different types of projections. These are just 3 basic ones. A cylindrical projection pretends that you're wrapping the Earth in like a toilet paper tube, and so you're going to have a whole lot of accuracy. If you put that cylinder right on the equator, you're going to have a whole lot of accuracy around the equator and less further north. A conic projection is just like that, laying a cone on the surface of the Earth. And so wherever that cone touches the Earth, you're going to have high accuracy. And as you move further from that, I think it's called a tangent. where you just touch something. Anyhow, but as you move further from that, you're going to get, you're going to have issues, right? Distortion. So projected coordinate systems have all of the components of a geographic coordinate system. So I would love it if you would list those components of a geographic coordinate system here. Yeah. And you can do that before me, or you can wait till after me. But one, they're going to have a spheroid that approximates the shape of the Earth. Two, they're going to have a point of origin. Three, they're going to have axes, x and y. And four, they're going to have units of measurement. So you can't get away from, I spelled measurement wrong. There we go. You can't get away from these elements. Every coordinate system needs these things. But in addition to those, coordinate system with a projection adds to these four items its projection, which is how the paper basically is laid around the Earth, and so how things are getting flattened. So let's see here. Let's talk about a few of the things here that we're dealing with, the types of distortion that we're dealing with. So we've got basically four types of distortion, and they're related to the properties of a map. So every map has properties that include shape. Did I spell that right? S-H-A-P-E. We've got shape. We've got distance. We've got direction. And we've got area. So those are properties of the feature on a map, features on a map, or properties of a map. And so one or more of these is going to be compromised every time you use a projection, and you choose a projection based on the choice of which matters the most, because every projection has some distortion, and many of them, if they're a really good projection for your area, they're not going to have much distortion at all. But every projection is going to have some distortion. For example, conformal projections are good at preserving shape. So one of the projections we might use for the entire Earth is the Lambert conformal conic projection. And so conic, it's having a sheet of paper around the Earth in kind of a cone, but conformal means it works to minimize distortion in shape. Okay, so that's what conformal means. I guess we could highlight that. Conformal, I don't even know if you can highlight in this program. It might just cause problems if I tried, but conformal means to minimize distortion in shape. Let's see, Molly-wide projection is good for maintaining an accurate area, but the shape is going to be distorted. And so we have, like I said, we have to choose a projection based on how the map's going to be used and what type of error won't interfere with that use. And so if we look at this next figure, we can see that there's a lot of different projections that are used, and this is just, there's more than this, but this is just an example of a few different projections and the way that they change the shape and relationship among the continents if you're looking at the entire Earth. So what we're going to do now, here's the fun part for the day. We're going to actually take a look at ourselves, what difference distortion can make on a map, and we're going to use the state of Washington because a lot of our mapping is going to be local and regional, and in particular, so when you go on the job, right, when you're mapping on the job, if you're in resource fields, agriculture, natural resources, water resources, and those sort of fields, most of your maps are going to be at the scale of a state or smaller, maybe occasionally up to the region, but really you're mapping, timber stands, you're mapping agricultural fields, you're mapping river systems. So we're going to be at a smaller scale, and so let's take a look at what distortion looks like at the kind of scales that we work at. So what we're going to do is we're going to get back into ArcGIS Pro, and we are going to create maps in each of these coordinate systems. And what I would like to point out to you right now is that we started our map with we started our project with a map in this geographic coordinate system, GCS NAD 1983. Okay, and that's the datum that's behind these next three maps. So the datum is the same, but we're just getting a different projection in UTM Zone 11 North, Washington State Plain North, Washington State Plain South. So that means that they use the same spheroid, they use the same origin, but they're projected in different ways. And then these next couple come in a different way. This one uses a different datum, the WGS 1984 datum. We'll talk a little bit more about that. Usually we're either using WGS 1984 or NAD 1983. Those are our two main datums. But this one is projected using a Webb Mercator projection. And then we're going to look at continuous equidistant conical that's supposed to help with measurements of distance, and then Albers equal area conic, which is meant to deal with issues of area. So with that, let's get into our map then and get some of these going. So the first one we want to make is UTM Zone 11 North. All right, so I'm going to go ahead and close out of this. We looked at our map properties. We're going to create a new map. I'm going to show you a quick, cheap, and easy way to make our own, to make a duplicate of our map. Oh, look at this. I forgot. I'd already added these for you guys. Oh, and I wanted you to make your own. Let's see here. Let me pause. Okay. That's fixed now. I want you to have a chance to actually set the coordinate system for each of these maps, and so I didn't want maps already there ready for you. Sorry, it'll give you a chance to kind of practice this. But what I was going to show you is an easy way to, if you want to create another map that looks really similar to the one you just have and already has the layers on it, you can right-click here under the Maps in the Catalog Project tab, Maps, and you can copy it, and then right-click and paste, and you can get a copy of the map you just made. This one I'm going to rename it to the coordinate system that I'm planning to turn it into, and so that's going to be UTM Zone 11 North. Okay. And hopefully the rename works. Sometimes I found that it takes me I don't know if it's because I need to press enter a certain way right after I rename something. UTM Zone 11 North. Enter. There we go. Okay. So, and it's here. I can't drag it onto my project, but what I can do is right click and hit open, and then it gives me another map tab. Now this one, we're going to make it in UTM. We're going to change it to UTM Zone 11 North. And the way we're going to do that is by going here, right clicking on the map, going down to properties, and then I'm going to make this bigger because I feel like it's easier to understand if we see the folders in their context. So right now it's NAD 1983, and that's a geographic coordinate system. The next, all the rest of the coordinate systems that we're going to put into this project are going to be projected. And so choosing a projected coordinate system folder, and then I choose UTM, and then I choose NAD 1983, Zone 11 North. So I'm in NAD 1983, UTM Zone 11 North. So what this is telling me is that my datum is the same as the earlier geographic coordinate system, but it's been projected using Universal Transverse Mercator System. The Universal Transverse Mercator System into Zone 11. Okay, bam. That was a big change, wasn't it? And so we've got the same 4 cities. Now we've got the state of Washington, but it looks a lot more compact now, kind of what we're used to seeing. All right, so that's 2. Let's go ahead and make our third. Right click, and we're just going to hit paste because I already copied. And we've got UTM Zone 11 North. Where are we going to make the next one? I think I said in here, Washington State Plain North. Okay, so let's go back to our project. WA State Plain North. Okay, enter. Okay, and so I'm going to go ahead and open this map. So we're just going to get tabs with a bunch of different maps in them. And I'm going to right click on the map, go down to its properties, and let's find state plane. So I think it's easier if I've got a little more space. So I'm going to close my geographic coordinate systems. I'm going into a projected coordinate system. So state plane is great for local mapping, mapping at the state scale or smaller. So rather than this stretched out geographic coordinate system, and this is based on NAD 1983, we want to base these all on the same datum so you can kind of see how the different projections work. And we're going to do that in US feet. NAD 1983 US feet right here. Okay, so you can see there's lots of options that are subtly different, but this is the one we're looking for, NAD 1983 with measurements in US feet. And then we have to find Washington State North. So you got all the states in the Union, and these are coordinate systems, these state plane that are commonly used by surveyors. State plane Washington North. We've got south and north, we want north. And then we'll hit OK, and bam, we've got a little different look. Boop, boop, you can see it kind of shift. Boop, 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 okay. And I'm doing all of these at a scale to 1 to 2,500,000. I don't know if you can see the scale down here. So these are all actually at the same scale. Let's do another one. Then we'll get some measurements going. All right, and so let's rename this one. And I think the next one we were going to do in state plane south. So WA, state plane, S for south, enter. And I'm going to add it to my map. Right click, open. All right, I'm added to my project here. Okay, so it's stretched out. It's not actually in state plane south, but let's put it in it by going down to properties, coordinate systems, and projected coordinate system. So finding the coordinate system you need sometimes takes a little bit, but I am actually showing you the most common coordinate systems that we're going to use. So that's going to be UTM Zone 11 North, State Plane North, and State Plane South. So let's see here. State Plane, NAD 1983 US feet, yes, whoop. And then State Plane, Washington South. Do-do-do. Do-do-do. Washington South, okay. Bam, and so very subtle. See that? Very subtle difference. Boop, 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 boop. Okay. And both at the same scale. Let's see what was after that. All right. I wanted to take a look at WGS 1984 Webb Mercator Auxiliary Sphere. You ask yourself, why do you want to do that? I will tell you why. And that's because this is the coordinate system that is used by most web maps, including ArcGIS Online and ArcGIS Pro, their base maps, all come to you in WGS 1984 Webb Mercator Auxiliary and the Auxiliary Sphere projection, okay? And they're supposedly they're good for viewing online. Let's take a look at what we see when we put a map in that projection. So let's rename this one Webb Mercator Auxiliary Sphere. So that's going to be WGS 1984 too. Okay. Enter, so that stays. And then we're going to add it to our map. And we need to change its coordinate system here. So, and this is going to be just like we said, everything we're dealing with now is projected. And so we're going to go to world projections here. That's where Webb Mercator is, if I remember right. And then we're going to go to, here we go. WGS 1984 World Mercator Auxiliary Sphere. There it is. So it's under our world projections, which you could see making sense if they're trying to project a base map that you can use all over the world. And so where was that again? Yes. Where was that again? It's under projected coordinate systems, world. And this is WGS 1984 World Mercator Auxiliary Sphere. I'm going to hit OK. Whoa, And this is still at the scale of 1 to 2,500,000, but now it's filling my whole computer screen and looks kind of chubby, north to south. But that's what we get. And then, let's see, I think I popped 2 more on here we wanted to add. USA contiguous equidistant conical. Okay, so let's do another copy or another paste here. USA contiguous, spell it, equidistant conical. Okay, and let's add that. Oh, did I press enter or just click away? I just clicked away. Whoops. So let's rename that again. What was I calling it? USA contiguous equidistant conical. Okay, USA contiguous equidistant conical. Okay, press enter so I don't lose my name, and let's add it to the map. And let's change its coordinate system. So these are all, like I mentioned, projected. And so we're going for USA contiguous equidistant conical. Oh, I can't even remember where I found that one. But I'm going to look for it. Continental maybe? North America. Oh, yep. Okay. Continental North America. USA contiguous equidistant conical. Yes, not Albers conical, but yeah, USA contiguous equidistant conic. All right. So what that looks like. Whoa. Okay. So this is meant for viewing the entire US. That's what this projection is for. You can kind of start to see the difference between projections that are kind of meant for looking at things in our region and those that are meant to look at things at a broader scale. All right, and then one more. Right click, paste this, and rename it. This one is going to be USA contiguous Albers equal area conic. USA contiguous Albers equal area conic. So this one's supposed to be an equal area. And press enter so I don't lose my title. And open it, add it to my project. And change its properties. And we'll hit, make this bigger. Boop. Close the geographic coordinate system because this one is also projected. Trying to retain a different set of issues or different set of distortions. Continental, North America, Albers equal area conic. Contiguous Albers equal area conic. Okay. And boom, we get something a little bit different. It's a little slight difference between equidistant and equal area. Okay, so now we're actually ready to do some measurements and see what so we can visually see what our distortion looks like, right? We got some differences here, but now let's kind of do some measurements so we can see that our orientation, like our direction of measurements is definitely different in this one than it is in this one, right? Like if you're looking at the degrees between, like the angle between Ilwaco and Medellin Falls, between here and here, that's quite a different angle, right? And you can also see that kind of some of the shape distortion. There's a geographic coordinate system, and there's Webb Mercator, and there's state plane. So we can visualize this, but let's do some measuring, all right? Okay, so now that we've set up these maps, we're going to be able to do some measurements and kind of get a feeling for what distortion goes on in with different projections. So we're going to start out with our geographic coordinate system, and we know that this doesn't look right with respect to area. Let's come up here to the measure tool, and of course we've got our notes here, and we're going to look at a few different measurements. Measurement kind of a straight line horizontal, so miles Spokane to Seattle, and then we're going to look kind of a diagonal from Ilwaco to Medellin Falls, and then we're going to look at the square miles in Pend Oreille County to kind of look at area. So we kind of can visualize and see the shape distortion, but let's look at some distance measures in an area. All right, so here's our measure tool. And we've got measure distance. And what we want here is distance in miles. And then we'll just click right there on Seattle and drag it and click right there on Spokane. And it looks like, what do I have a sum going on there? I'm going to double click on Spokane to end it. Looks like we've got 246.2 miles. So we can fill that in, right? If we have our fill-in thing going on. 246.2. All right. And then let's take a, oh, did I just make it disappear? 246.2. All right, and then the next piece, let's look from Ilwaco to Medellin Falls. So we'll clear that measurement. And then we'll click on Ilwaco, and we'll double click right on Medellin Falls. Looks like 358.12. We also get the bearing. Ooh, we should write that down too, 58 degrees, because I wonder how much that shifts with the different projections. So the bearing is 58 degrees and the distance is 358.12. So 358.12 miles and 58. Oh, getting the symbol for degree is a pain, so we're just going to type in degree. There we go. Okay. And I think the degrees is going to change as we see the angles of the maps changing. And then square miles of Pend Oreille County. Let's see here. So that's going to be distance. We're going to measure the features. That'll give us the full area. And what we want is square miles. So this is measuring the whole feature in square miles. That way we don't have to click around the whole boundary. And so Medellin Falls, or Pend Oreille County lights up there. And it looks like it's 1425.72. Also gives us a perimeter. 1425.72. 1425.72. Okay, except for 1425.72 square miles. And we actually already have square miles written in the question, so we don't actually need to type it in there and take extra space. Okay, interesting. Let's take a look at UTM Zone 11 North, see if there's any differences there. And then what I'll do is I'll just kind of stop the recording for a minute. I'll finish filling out the table and we'll talk about what we see so you know how to do it. You can just do it on your own. But let's do one more. Let's do UTMs here. So we're going to do that we're looking at miles between Seattle and double click on Spokane. Looks like 246.3. 246.3. Come on. 246.3. And then let's look at the miles from Ilwaco to Medellin Falls. That's going to be, boom, up to here, double click. And that's, oh, whoops, I forgot to erase. So if you don't erase, the miles are going to add up, and then you just have to look at your segment. So I think it's simpler just to erase. Okay, 358.22 at 63 degrees. 358.22 at 63 degrees, bearing. Okay. Interesting. We see a difference there, don't we? Yeah. Okay, and then the square miles in Pend Oreille County. So we'll erase this, choose our measure feature tool, select square miles, click on the county, 1424.6. 1424.6. 1424.6. Okay. There we go. All right, so I'm going to go ahead and pause the recording and run through the rest of these, and then you know how to do it, so you should run through the rest of these, finish filling out the table, and meet me back in a minute, and we're going to see what some of the differences are, okay? All right, so I've finished filling out the chart here and doing the measurements on the map. And what you can see is the miles from Spokane to Seattle is right about at 246 in the geographic coordinate system, and then in our kind of our local systems. When we go to a world system where we're a projection that's meant for visualizing the entire world, we get something like 364 miles. If we go to something that's looking at our continent, we're back in the ballpark of what seems to be the actual measurement. Interestingly enough, if we compare it to what Google says Spokane to Seattle, not driving, but straight line distance is 229 miles. What might be going on there is that the dot that's placed on my map isn't the same place that Google calculates as the center of Seattle. That might be what's going on there. But just to be honest, we get 229 when we ask Google how far that distance is, straight line. So, like I said, I think that might just be dealing with a different location of the city dot. When we look at the difference between the distance between Ilwaco and Medellin Falls, our local coordinate systems aren't too different with respect to the distance, but then you can see that the degrees is different. So that kind of looks at like the angle that Washington is sitting at. If you go to our global projection, we've got a much different distance, although the angle isn't different. And then we have a slightly different distance and a different angle if you're looking at the entire continent, a projection that's meant to be dealing with the entire continent. And the square miles for Pend Oreille County, Google says it's 1425 square miles, and most of our measurement systems tell us it's 1425. The ones that are way off are going to be the global one, which our areas and our distances are much larger, apparently, for this part of the world than the reality is. And then our continental scale projections, 1439 for so these are two very similar projections. They're conical projection meant to be used with the contiguous United States. But the difference with this last one here is it's an equal area projection, which means it's supposed to preserve the area of features. And we can see the area of Pend Oreille County is supposed to be about 1425 square miles. And with this equal area projection, even though we're looking at something that's that's meant for the scale of the continent, we still have area is preserved. So that's kind of fun to see. And then area is a little bit inflated here with the just the equidistant projection. So interesting. So we've kind of seen what difference distortion makes in real life at the scales that we tend to do our maps at. And what else did I want to say about that? Yeah. So the coordinate systems that we're most commonly going to use, we're going to talk about these in just a minute, but for the areas that we're mapping, we will most often be in UTM Zone 11 North, Washington State Plain, and at Washington State Plain either north or south. If we're looking at a larger area, like if you're going to do a map of a broader area, maybe the whole US or several states, then you could start to look at some of the continental scale projections. But we will spend most of our time in these three projections, and what you can see is there are slight differences. So there you go. But not huge distortions. So those are good ones for our area. Okay, so what do you need to know about projections to make maps for in this class? So if your map is at the scale of a city, I recommend using state plane projection. And every state has their own, usually have a couple. If you're Spokane and north, use the north projection. If you're south of that, use the south. So Washington State Plain north. If you're in the city of Spokane or north. If your map focuses on a region, UTM projections, universal transverse Mercator. Okay, UTM projections are good for the UTM zones they're in. They have very minimal distortion if you're within the zone, and the measurements are all in meters, which can be super useful for navigation. In fact, if I understand right, if I remember right, a lot of our military maps are in UTMs. So those are good for navigation. If you want to create a map at the scale of a continent, you have to decide whether you want the area, the shape, or the distance to be preserved. So you have to decide where you want your distortion. If you want the area to be preserved, an equal area conic like Albers equal area conic is a good one, and we worked with that in our exercise there. If you want the shape to be preserved, Lambert conformal conic is good. A conformal projection is one that preserves shape. Lambert conformal conic is a good projection. And then if you want distance to be preserved, we didn't show this one in the map we've been working on, but a good projection if you want to preserve distance and you're working with a larger area is going to be the Platt-Curie projection. Now, if you were getting like a degree in geography and GIS, like a full 4 years of just doing GIS, you would have an entire class that was on coordinate systems. You'd take a whole semester on coordinate systems. But because we're like doing all GIS in 1 quarter, this is kind of what you need to know to just kind of work in this class and kind of get on your feet and get moving. So some suggestions for if you are doing maps that are outside the area of our region. These are some good quality projections. If you want to create a map at the scale of a continent and shape, area, and distance are not critical, you're going to want to choose something that's kind of a compromise where you have just a little bit of area and error in each of those. And so for that one, a cylindrical equal area projection is good. So it kind of, it's like a compromise projection. Sometimes you know what's most critical, and sometimes it's like, well, I don't really want any fudge in any one area, but I can take it in a few just a little bit. So here's something that's important to note about your map. So we've already been into ArcGIS Pro, and we've looked at the coordinate systems of these different maps, right? We right-click on them, we go down to Properties, we take a look at coordinate system, and this one is in UTM Zone 11 North, right? So that's how we find the coordinate system. If we don't set the coordinate system for our map, that map is going to take on the coordinate system of the first layer that you add to it. All right? So that's going to be the default coordinate system. So the map is going to take on the coordinate system of the first layer you add to it. If you want to set the coordinate system for your map, you're going to right-click on the map title, just like we did, choose Properties, and go to the Coordinate System menu. I'll capitalize that to make it stand out. Okay, so just like we did. And then let's see. So that little pane there shows the of the map. I'm going to say shows the current coordinate system of the map. All right. This over here, so under the layers, you can see which layers are in each coordinate system. So in this particular example, we've got two layers on the map that are in Clark 1866, and we've got one layer that's in NAD 1983 Harn, State Plane, Washington South, or we just call it State Plane South, and then we've got one layer, the base map, that's in WGS 1984 Web Mercator. So that kind of talks you through which layers are in each of the coordinate systems. So we can see we've got a map that have, and we'll actually, let's talk about this in a minute, but you can see we have the layers are in a couple of different coordinate systems. They were created in a couple of different coordinate systems, but we can put them on a map that's all in this coordinate system. Let's talk about that in a minute. It's called projection on the fly, but we need to talk about that because it takes a little bit to kind of start to understand that concept. But I did want to point out here that look at that. We've got layers on this map, and it's just the same map we're looking at over here. And these layers are in different coordinate systems. Let me just show you that here. So here, so this map is in UTM zone 11. And if I go into my layers to look at their coordinate systems, my 4 Washington cities are in Clark 1866, and my State Plane Washington and my Washington counties are in State Plane Washington South. So both of the layers on this map are not in UTM zone 11 North. I think I just accidentally changed this map back to. Okay, and so get back into UTM. 1983, zone 11 North. Okay. So what I was going to say is the map is shown using the coordinate system UTM zone 11 North, but these 4 cities are in Clark 1866 and the counties are in State Plane. What's going on here? It's called projecting on the fly. And what it means is it's one of the powerful things that GIS software can do for us. What it means is that the software is taking each of these layers and adjusting and transforming them so that we visualize them, and what we see on the computer screen is UTM zone 11 North. And so that is probably one of the biggest powers that ArcGIS has, is it can take spatial data that's in any coordinate system and it can show it in the coordinate system that you choose for it. So it hasn't changed. Like if I were to look over here, Washington counties, and I'll kind of show you that in a minute. So if I'm to go over here and I were to look at Washington counties, which over here, if I were to right click on them and go to properties, Washington counties, I'm going to look at the spatial reference, are in State Plane Washington South. Okay, so it's still in State Plane Washington South, the data that's stored in my geodatabase, but it's shown on the map in UTM zone 11 North. I'll come back to this. Let's take a few more notes and I'll come back to this. Okay, so the only other thing we wanted to say about this illustration, this little pane, was that we can change the coordinate system of the map here by, let's see, and of the map here by selecting from a new geographic or projected coordinate system. All right, so that's what we can do there. Okay, so, and I started to address this already. Can I add a layer to my map if the data was created, as all spatial data has to be created in some coordinate system, but can I add it to my map if it was created in a coordinate system that's different from what I've assigned, the one that I've assigned to my map? Any guesses? The answer is yes. So every GIS project basically has 3 things going on relative to your coordinate system. So you have the coordinate system of the data in each layer of the map. Let's go take a look at that again. So here I'm hanging out in UTM zone 11 North. That's what my map is in. But I've got this data here. Let's look at the 4 cities Washington. If I go over to the data that's used on the map and I go to properties of that data and I look at its spatial reference, the coordinate system here is a geographic coordinate system, and it's Clark 1866. There we go. Okay. But the map isn't Clark 1866, which means these cities are being displayed on the map by being projected on the fly. Okay. So let's take a look at our notes again. The coordinate system of the data, each layer on the map. So we can find this. Let's see. Whoa, I don't know how I did that. Okay. So we can find this by looking in the catalog at the, we can find this by looking in the catalog at the spatial data and checking its properties. All right, so we've got the coordinate system of the data in each layer on the map, and we can have several coordinate systems. Each layer could be in a different coordinate system and be on a map that has a different coordinate system than those. Then we've got the coordinate system of the map, and we can find that by right-clicking and checking on the properties of the map. And this one is at UTM Zone 11 North. I don't know why it keeps on copying and stuff from the past. We can find this by looking at the properties of the map in the contents pane. Okay, and then the coordinate system that each layer on the map has been projected into. And so that's called projecting on the fly. On the fly. Okay, and so this means that every layer shows up in the right location. GIS transforms it, say each layer, from the coordinate system it was created it in to let's see, to visualize on the map in the map's coordinate system. Okay, so make that a little bit smaller. Okay, so the coordinate system that each layer on the map has been projected into. So ArcGIS, just as you put things on the map, automatically on its own is going to take them and it's going to translate the information it was given for the coordinate system it was collected in. It's going to transform that so it looks right on the map in the coordinate system you've defined for the map. Okay, that's called projection on the fly. And here, ArcGIS used mathematical models to translate spatial data from one coordinate system into another. This is called on-the-fly projection. On-the-fly projection, or projection on the fly. It just means it's, doing it as you go. And it is one of the powerful features of ArcGIS. Yes, I said that. So what does that mean for us? We can create a map and we can put our map in any coordinate system that works for the area, and we don't need to worry about modifying each of the layers that go into that map. We don't need to change their coordinate system to match with the map. As long as they have a correct coordinate system that they were collected in and it has all the features of a standard coordinate system, ArcGIS will read that in and automatically show them on the map in the coordinate system that we have defined for the map. So then, kind of the last piece of this lecture, and in fact, maybe I'll pause this for a second so we can break the lecture in a couple pieces so it's easier to digest. But we're going to talk about, the next thing we're going to talk about is when you might run into trouble and how to fix that, okay? We'll do that in the next little segment just to keep this from getting too long.